Hello and welcome to our lesson on characteristics of graphs of rational functions. We're actually not going to be looking at anything new today. We have looked at characteristics of functions before, and when I say characteristics, I'm talking about things like domain, range, and behaviors, where the graph is increasing, decreasing, constant, positive, negative. So these things we've talked about before. But we want to go a little more in-depth in this particular module with just the rational functions. So that's what we're going to do. Brush up on some vocab we've talked about before and look more in detail about those topics as it concerns rational functions. Okay? So let's talk first about the domain. The domain for any function, the domain of a function, represents all x values for which that function is defined. So any x value that you could plug in that would produce a y value is going to be included in the domain for that function. Now we know polynomial functions have no restrictions. So for example, like y equals 2x plus 1. I can plug anything I want in there for x and a y value is going to be produced, which is why we see on that graph of that linear function a graph that goes left and right forever without any breaks. Now that's not going to be true for a rational function. If we have a fraction of polynomials here, we have to remember the restriction for fractions, and we've been talking a lot about this in this particular module. We know that the bottom of our fraction can't equal 0. So any x value that makes that denominator equal 0 creates either an asymptote in the graph, or if it reduces out, it creates a hole in the graph. But either way, that x value is not defined for that function, and then is not included in that graph. So for a rational function, our domain has to exclude the restricted x values. And we can find those whether we're looking at an equation for a function or we're looking at the graph. So here we know that 3x minus 6 cannot equal 0. So if we were to add 6 over, that means 3x can't be 6. And if we were to divide both sides by 3, that means x can't be 2. X can't be 2. That is the restricted value from this function. It would make that denominator equal 0. So we could say our domain in two different ways. We could say our domain is all x's such that those x's cannot equal 2. That was our set notation, if you recall. Or, what I like better, so that's what I'm going to put here, if x can't be 2, what can it be? It can be, think about your number line graph here, it can be anything before 2, it can be anything after 2, it just can't be 2. So in interval notation, which is more common, we're going to say this domain is everything from negative infinity up to 2, united with everything from 2 to infinity. And as long as we're keeping the parentheses on the 2 there, then we're excluding it. Remember, the bracket would be to include the 2, and we don't want to do that. So there it is, everything but 2. That is the interval notation for everything but 2. Okay? Let's look at the next one. Same concept. We know our denominator can't equal 0. So if 2x squared minus 18 cannot equal 0, let's see, if we factor the 2 out of this, hopefully you're recognizing this is factorable, we have a difference of squares left. So x squared minus 9 becomes an x plus 3 and an x minus 3. And if that can't equal 0, then we see here x can't be negative 3. And we see here that x can't be positive 3 because those would make our zeros. So our domain has to exclude negative 3 and positive 3. So again, think about a number line graph, okay? We can't be negative 3, we can't be positive 3, but I can be everything before negative 3, everything between those values, and everything after 3. So this domain is going to have 3 intervals. Everything before negative 3, that's negative infinity to negative 3, united with everything between negative 3 and 3, and then we're going to unite that with everything after 3. Again, as long as we keep parentheses on all those 3's and negative 3's, then we're excluding them from the domain. Okay? Alright, this last one, if you feel good about this, is one for you to try. Instead of giving you the equation for the function, I've given you the graph, but hopefully you can still see the restrictions for x. So this vertical asymptote here and this vertical asymptote here is telling me that x cannot equal a positive 2, and this one's telling me that x cannot equal a negative 2. So whatever the function was, it had in the denominator a factor of an x plus 2 and a factor of an x minus 2. So this domain can be everything before -2, which is everything from -infinity to -2, everything between -2 and 2, so -2 to +2, and everything after +2, so from 2 to infinity. Okay, so that's our domain. The domain has to exclude the restrictions for x. And it's similar for range. Range is all the y values for which our function is defined. And so if we have a restriction for y, then that has to be excluded from the range. So the range is the y values. And the range for rational functions, again, has to exclude any y values that are restricted. The restricted y values. Okay, now here, just to point this out again, the restricted x values, those ones they cause vertical asymptotes, or they could cause holes in the graph. What do we see on the graph when we have a restricted y value? Well, we see, instead of a vertical asymptote, we see a horizontal asymptote. So we're looking at horizontal asymptotes. If we can identify where the horizontal asymptote is for our function, we can see where our restriction would be. Okay? So the first example here, if we look at the degree of our numerator and our denominator, the degree of the top is 1, and the degree of the bottom is 2. And since the degree of the numerator is less than the degree of the denominator, then this one is going to have a horizontal asymptote at y equals 0, just like the parent function. Now, if you weren't sure, and really you could have done this earlier too, if you weren't sure, because sometimes it's hard to remember all those rules, let's go ahead and get this function in so we can just confirm that there's, yeah, we can see it. You see the horizontal asymptote at y equals 0? Right? You see how the graph's got that barrier there? So that's got to be a restriction then for our y values. So if we have a horizontal asymptote at y equals 0, that means y can't be 0, then our range has to exclude 0. So everything from -infinity to 0 united with everything from 0 to +infinity is our range. Okay? How about the next one? The degree of the numerator this time is 3, and the degree of the denominator is 1. What happens when the degree of the numerator is bigger than the degree of the denominator? Well, if it was exactly 1 more, we could be looking for an oblique asymptote, but this denominator is 2 more. So this is not going to have a horizontal asymptote or an oblique. There is no horizontal asymptote here. So what does that mean? Well, it should mean that there's no restrictions, but again, let's just look at this. If I have 5x cubed, let's see, plus 2 over x plus 4, then we have a graph that goes up and down forever. There's no restriction on the y. So there's no horizontal asymptote, there's no restriction on the y. That means that this range is anything from -infinity to infinity. And again, if you weren't sure, just put it in the graph, put it in Desmos and you'll see the graph, okay? Now the last one, if you feel good about this, give it a shot. I can see the restriction here. This is a horizontal asymptote at y equals 2. So if we have a horizontal asymptote at y equals 2, that means our graph can't get to a y value of 2. That means our range has to exclude that y value of 2. So this range is going to be everything before 2, which would be -infinity up to 2, united with everything after, which is from 2 to +infinity. Okay? And that's that. Okay, domain and range, not so bad. Just exclude the restricted x's from the domain and exclude the restricted y's from the range. Now, hopefully you can find those restrictions looking at the function or looking at the graph. If not, put it in Desmos and try to figure it out that way. Okay? Alright, how about end behaviors? Again, this is something we've talked about before. If you recall, end behaviors describe where the y values of the graph are going. What are the y values of the graph approaching as you follow the ends? Okay, so for example, on number 5 here, when it says, as x goes to infinity, if we were on the x-axis heading toward infinity, we would be going to the right. So this says follow the right end of the graph and tell me where are the function values, where are the y values headed? Okay? If I follow the right end of this graph, this is the right end. If I keep following this way forever, what's happening to those y values? Well, they're going to get closer and closer and closer to this horizontal asymptote. And that horizontal asymptote is at, looks like, -3. So what's happening is if the branch gets closer and closer, that means the y value, right? The y value is getting closer and closer to that -3. So our graph is approaching the horizontal asymptote at -3. Right, this horizontal asymptote, let me change colors here. Sorry, horizontal asymptote at y equals -3 is what both ends are actually approaching, right? So this one, if we were on the x-axis going toward -infinity, that's saying go to the left. Well, if we go to the left end of the graph, what is it doing? Well, it's still approaching that same asymptote. So these y values are getting closer and closer to that y value of -3. Okay, so both ends are going to be approaching -3, and really every time you have a horizontal asymptote in your graph, your ends should be approaching that horizontal asymptote. Okay, so the same thing is happening here. I've got this end approaching the asymptote, I've got this end approaching the asymptote. So where's the asymptote? This asymptote, and that, again, the horizontal asymptote is at y equals 4. So both ends are approaching both ends have y values that are approaching 4. Okay. Now if you look at number 7, this one doesn't have a horizontal asymptote, it has an oblique asymptote. So the branches are still approaching the oblique asymptote, but think about where these y values are headed. If I go to this end of the graph, what's happening to these y values as they follow that asymptote? Well, these y values are continuously going up. Okay, and then what happens with these ones? So this branch is going to continue to follow the asymptote, which is going down. So right, we see this one going down forever. It's not the same as the horizontal. The horizontal asymptote means those y values are restricted, but here we see branches that are going to go up and down forever. So I swear I chose eraser. Sorry. So here, as we go to the right end of the graph, the right end of the graph was this guy. We said that those were going up toward positive infinity. And then as we go to the left, this guy down here, these y values are going down toward -infinity. Okay? So if you have a horizontal asymptote, your ends should approach that horizontal asymptote. If you don't, then it's most likely going to be that your ends are either going up or down forever, and that's what we see happening with the oblique in number 7. Okay? Alright, what are we reviewing next? Let's see. Increasing, decreasing, positive, and negative intervals. So increasing intervals are parts of the graph where increasing intervals are parts of the graph that are going up from left to right. Sometimes I get ahead of myself and I get, I'm so excited to teach this math to myself in my kitchen that I start talking too fast. I'm sorry. Okay, I really wish I was in a classroom talking to people instead of myself here, making myself laugh. My dog might be. Nope, he's passed out. Okay, back to notes. Decreasing intervals are parts of the graph that are going down from left to right. And that's pretty intuitive, but those often get confused with positive and negative intervals. So positive intervals are intervals of graphs, or intervals of the graph that contain positive y values, which means they will be above the x-axis. And then negative intervals are parts of the graph that contain negative y values, which means they will be below the x-axis. So increasing, decreasing, these have to do with behavior. What's happening to the graph? Is it going up? Is it going down? And the positive, negative, this is really just about location. Is it above the x-axis or below? Okay, so gotta be really careful to distinguish. Now, the concepts themselves still really aren't that bad. We just have to make sure we accurately give the answer. So just like domain, if I'm asking you for the domain of the graph, you're giving me the interval of x's where the graph is. These intervals are all given using the x values where they start and stop. So each of these intervals will be given using x values, so we'll use the x-axis as our guide. Okay, so let's read this graph. So this first branch, left to right, is definitely increasing. And that's a terrible color. Eraser. This is definitely increasing. Now if I jump over to the next branch, again we read left to right, so we still have a piece of the graph here that is increasing. And then it turns, right here it turns. So as it turns, now when we're going left to right, it is decreasing. And then we got to jump over that asymptote and deal with the last branch, which left to right is also decreasing. Okay, so we've got two intervals that are increasing and two intervals that are decreasing, and I want to use the x-axis as my guide to identify those intervals. So let's see, I have this first piece, I'm trying to use a different color. Okay, so this first piece that I highlighted as increasing corresponds with these x values. So we'd say from negative infinity up to, that asymptote is at -1. So it was increasing from, we had negative infinity to -1, and also, so we can put a union there to unite these two groups. The next piece is increasing in this little section of x values here, from the asymptote to that turning point, so that's from -1 to 0. -1 to 0, and remember when we give these intervals we'll always use parentheses because we won't be increasing or decreasing at a point, but we will over the interval, so we don't want to include those endpoints. Okay, so let's see, get rid of this. Alright, now the next two pieces that are decreasing. So this first piece that's decreasing is over this interval of x values. That's from 0 to +1. So from 0 to +1, and then the other interval, the other decreasing portion, goes with this interval of x's, which starts at 1 and goes forever toward positive infinity. So 1 to positive infinity. Okay, hopefully that makes sense. And now let's look at positive versus negative. Remember, this is just about location. What pieces of the graph are above the x-axis and what pieces are below. So we clearly have a piece, a branch, guys. We have a branch here that is above. We have another branch here that is above. Both of these, because they're not going to go below that asymptote, are going to be positive intervals because they are above the x-axis. So this is positive, this is positive. Now the other one we got to be extremely careful with because this point right here is actually on the x-axis. So that particular turning point there is neither positive nor negative. But everything before that point, this little piece before that point, what am I doing? Sorry, this piece is definitely negative, and this piece is definitely negative, but I have to make that two separate intervals because of the point where it actually hits the x-axis. So this piece is negative, this piece is negative, but this point right here on the axis isn't negative or positive. Isn't positive or negative. So we have to exclude that point, okay? So positive, let's see. Positive, the first piece, it looks like it goes with this interval of x values from negative infinity up to -1. Negative infinity up to -1. And then the other positive portion is with these x values, so from 1 to infinity. Okay, and then negative is going to be broken again into two separate intervals. So before that point where it hits the x-axis, and then after. So from -1 to 0, and then 0 to 1. -1 to 0, and then 0 to 1. -1 to 0, and 0 to 1. Again, we have to separate because that point is on the x-axis, so it isn't positive or negative. It's 0, has a y value of 0, and 0 doesn't have a sign attached. Okay? Alright, I got one problem here where I just kind of want to put together all of the things that we've done here so far. So we're going to try to graph this guy. We're going to try to identify all the characteristics, and then yeah, hopefully we'll be well on our way to finishing up this module. Okay, so vertical asymptotes. What's going to make this denominator x squared minus 4 equal 0? Well, this factors into x plus 2 and x minus 2. Make this bigger. So we know that we're going to have a vertical asymptote at 2 and negative 2. And this, I'm going to move this, just ran out of space. So at negative 2 and at positive 2, we're making the denominator equal 0. Those are technically the x values that we can't be. So we're going to have a vertical asymptote at x equals 2 and x equals negative 2. Okay, to find the horizontal asymptote, we're going to compare the degree of our numerator and denominator. So the degree of the numerator is 1, and the degree of the denominator is 2. Anytime the degree of the numerator is less than the degree of the denominator, it's going to be like the parent function, which has a horizontal asymptote at 0, so y equals 0. So we have domain and range. We should be able to just exclude the x's there and exclude the y there. But let's go ahead and confirm what we're doing in the calculator before we go any further. So Desmos, let's see, y equals 3x over x squared minus 4. So we have, let's see, vertical asymptotes. We said 2 and negative 2. So x equals 2, x equals negative 2. Horizontal at y equals 0. Everything looks good there. And let me just make these all dotted. Okay, so I think we're in good shape. There's our graph. Now, the domain, we can see those vertical asymptotes that we did were correct. The graph is never going to get to those x values of 2 or negative 2. So we want for our domain to exclude 2 and negative 2. So everything from negative infinity up to negative 2 united with everything from negative 2 to 2, that was between, and then that's going to be united with everything after 2, so 2 to infinity. Okay? Now the range is a little tricky here because this actually might have happened on the one in the front. I think I just wasn't paying close enough attention. Now, we have a horizontal asymptote at 0, but you see what's happening with this piece in the middle? It actually has a point at 0, so there is a portion of this function that does include a y value of 0. So while the outside branches aren't going to get to 0, the piece in the middle does. So this time the horizontal asymptote doesn't actually create a restriction for the y values. So the end branches aren't going to get to y equals 0, but the middle piece goes right through it, which means we don't have to exclude a y value of 0 because there's graph everywhere. Every y value is covered by this graph. So let's get this on the paper here. We had negative 2, we had positive 2, and the graph was not getting to either of those values. And normally y equals 0 would have created a restriction, but we had this piece in the middle that actually has a y value of 0, so it kind of does this. Oops, let's try this again. It's kind of doing this snaky thing here, but because that y value of 0 is defined in the middle, we don't have to exclude it. And then where were the other branches? Oh, my calculator froze. Okay, sorry. So the other branch is going to be here. And the last branch is going to be here. Okay, so domain, we're covered. Range is going to be everything from negative infinity to infinity. So even though we have that horizontal asymptote, again, it's not a restriction because we see that middle piece actually has a y value of 0. Alright, in behaviors, we can see, hopefully, that this end is approaching a y value of 0, and that this end is approaching a y value of 0. So both ends are headed to that horizontal asymptote at 0, so y values of 0. And now let's look at these intervals. So negative infinity to negative 2. Negative infinity to negative 2. negative infinity, negative 2 is this interval of x's right here. So what is happening for this piece of the graph? Is it increasing or decreasing? Left to right, definitely decreasing. So let's check that box. Okay, how about negative 2 to 2? Negative 2 to 2 is this interval here. Left to right, what is this graph doing? It is decreasing. Okay, how about 2 to infinity? 2 to infinity, this interval here. What is this graph doing left to right? Still decreasing. Okay, all of these pieces are decreasing. Alright, how about positive versus negative? Okay, negative infinity to negative 2. That's again this interval. Is this piece above or below the x-axis? Well, it's below, and so we're going to say that that is negative. How about negative 2 to 0? That's this piece right here. That is above, so that's going to be positive. Okay, 0 to 2. 0 to 2, that's this interval, so this piece, which is definitely below, so that's going to be negative. And then 2 to infinity. 2 to infinity is this interval, so it corresponds with this piece. That's definitely above the x-axis, so that's going to be positive. Okay, hopefully all of this makes some sense. Hopefully it's good review for us. I think the only tricky part there was that horizontal asymptote that got crossed on this last problem. But otherwise, again, just review. Okay, so you got some practice problems to work on. If you're struggling, just let me know. I'm here.